Have you ever looked at a car or a plane or really any complex machine and just wondered, how do they even start to build that? I mean, before a single piece of metal gets cut. Today, we're pulling back the curtain on that digital blueprint. Seriously, think about it. Your phone, your car, these things are marvels. But how do you go from just an idea to something that actually works? Something that's not going to fall apart the first time you use it and that can actually be built? Well, we got our hands on a kind of secret blueprint. This right here, this is the official teaching plan for a university course called Modeling and Computer Analysis. And it lays out the entire playbook, week by week, for how they teach future engineers to build the world of tomorrow, all inside a computer. So let's break it down. We're going to follow a student's journey right through this course to see how they go from basically a blank screen to a fully designed, fully tested virtual machine. And it all starts with one absolutely critical piece of technology. That technology is computer-aided design, or as you'll hear it called CAD. Just think of it like a super-powered digital toolbox. It lets engineers sculpt, build, and test their ideas with incredible precision, long before anything physical even exists. And mastering these tools, that's what this course is all about. So where does this whole journey begin? Well, it's actually in a surprisingly simple place. Before you can build some wild, complex 3D machine, you have to learn how to draw a simple, flat, two-dimensional shape. Now, we are not talking about just doodling. Students learn the very strict rules of technical drawing, but they're doing it inside professional-grade software like Kia and SolidWorks. You know, the same tools used in the aerospace and auto industries. It's all about building that rock-solid foundation. And the process is very methodical. First, you draw the basic 2D shape. Then, and this is key, you lock it down with precise dimensions and what are called constraints, which are basically just rules that define how everything connects. The software even helps you find errors. Once it's perfect, it's ready for the next dimension. And okay, this is where the real magic starts to happen. We're leaving the flat world of sketches behind and jumping into the solid, three-dimensional world of parts and machines. You take those perfect 2D profiles and you give them depth. You can extrude them, revolve them, basically sculpt them into individual components. You know, a gear, a bracket, a housing. Each one becomes its own virtual, solid object. And once you have a collection of virtual parts, what do? Well, you build something. This is the assembly phase. It's like a high-stakes digital Lego set, where students bring all their components together to build their final machine, piece by piece. This whole process mimics a real factory floor, but it's all happening on a screen. Students add their parts, then they apply rules that say how they connect and move. Like, can this part slide? Can that one rotate? They can check if parts are bumping into each other and even create those cool exploded views you see in instruction manuals. Okay, so you've designed it, you've built it virtually. But the biggest question is still out there. Is it actually going to work? Or maybe more dramatically, is it going to break? I mean, this is the critical question for any engineer. Building a physical prototype just to watch it fail is incredibly expensive and it takes forever. Luckily, this modern software has an absolutely incredible answer. It's called structural analysis. You basically tell the computer where the part is held in place. Then you apply the forces it would see in real life. You hit go, and the software runs millions of calculations to simulate the stress. And what you get back is this color-coded result that shows you exactly where the weak points are. And the insights you get are so deep. Students learn to read data on how much the part bends, how far it moves. They analyze really complex stuff like von Mises stress, which is basically a fancy way to find the exact spot where a material is going to fail. And most importantly, they calculate the factor of safety to make sure their design isn't just strong enough, but way stronger than it needs to be. So, how does all this cool tech prepare someone for a career? Well, that's the whole point. This course isn't just about learning software, it's about getting students ready to solve actual, real-world problems. Every single skill, sketching, modeling, assembly, analysis, it's all funneling toward one goal. Being able to take all that knowledge and solve messy, complicated problems that don't have easy answers, just like in the real world. And the proof is right here in how they're graded. Get this, a full 50% of a student's final grade comes from problem-based learning projects, half their grade. It's all based on applying what they've learned, not just memorizing it. And being a modern designer is about more than just being good at CAD. The syllabus shows that they also have to understand things like project management and cost analysis. They have to think about timelines and budgets, because the best design in the world is useless if it's too expensive to actually make. I love this quote. It's pulled right from the university's own notes. The whole goal is to tackle real industrial issues, to make students ready for the job from day one. That link between the classroom and the real world is completely intentional. And speaking of the real world, I found this fantastic little note in the course feedback. It points out that excessive Monday public holidays were disrupting the teaching schedule. It's just a small, human detail that reminds you that even a high-tech engineering course has to deal with the calendar. So from a simple 2D sketch to a fully analyzed 3D assembly, that's the journey. It's a systematic process that really does transform a student into a creator, someone who has the digital tools and the critical thinking to design the next generation of products. It really makes you think, doesn't it? These tools give you the power to build almost anything you can imagine, and to test it before it even exists. So, the final question is, if you had that kind of power, what would you create?